Hello, everyone. So this class, we're going to continue with our computational methods in engineering. And specifically, we're going to jump into a new section of this class, which is talking about the probability in engineering. So we're going to learn about different probability functions and also how how we apply the idea of probability when we're evaluating different environmental systems. So first, we want to give a few definitions. So first is that in engineering, we want to define this probability called the exceedance probability. So basically, it tells when the engineering system will fail, right? So basically, in these systems, we will define this probability PE, which basically is the exceedance probability, or we also call them as the risk of failure. Right. So for example, if you have a high exceedance probability, let's say 90%, right, the risk of failure or this value is 90%. Okay. And the reliability, which is sort of the reciprocal of the exceedance probability, is just going to be 100% minus PE. Basically, it's reliable for 10%. And of course, we want a high reliability of any engineering system. So that's why we want a system that has a smaller PE. And based on the PE, people also define the parameter called the return period or return time, which will generally describe how long the engineering system can hold reliable, right? So if you have a PE of 0.01, right? So then the return period will be 1 divided by 0.01, which is 100. And of course, here it's going to depend on what is a unit we're looking at. It could be 100 years, or it can also be 100 milliseconds, right? So then it really depends on how we define our exceedance probability here. And later you will realize that for a lot of engineering systems, since we are expecting them to run for a long period of time, so that's why the PE is defined based on years. Okay, so basically for here, we're specifically talking about sort of the unit calculation of the exceedance probability. For example, the PE of 1 year, right? But then the thing is that we want to calculate, for example, the risk of failure for the entire time, right? So for the entire working life of an engineering system. So that's why we define this basically this or specify this PE further as the annual exceedance probability, right? So it's every year, what is the risk of failure? And for example, a system can have a design life of n years, right? For example, 20 years. And then the risk that the system will fail within its design life. We can calculate that. Basically, we want the system to be working, right? So to be reliable for each year. Let's say we're trying to look at 9 years. So here I have 9 blocks, right? So the risk that the system will fail, or let's say the risk that system can be reliable over the 9 years is going to be 1 minus PE, right? It means that it can go through the first year, second year, the same thing, 1 minus PE, third year, fourth year, fifth, 6, 7, 8, 9, right? So the probability of having a reliable system over 9 years is going to be 1 minus PE to the power of 9, right? Or to the power of n. So the risk that the system will fail within its design life is just going to be 1 minus this reliability over n years, right? So this PF, F stands for the risk of failure, right? So then, based on the definition we had here, right, the return period is just 1 over PE, right? So we can put 1 over T over here. And further, when we define, for example, let's say we're trying to look at the design life of n years. So it's going to be, or basically the n is just going to be 1 over T, or right? So the n is just going to be the time T, right? It's the duration or the return period. Let's say if we wanted to have the system that can run for 20 years, right? So then the design life is 20 years, and T here we'll put in 20 years, right? So basically we can simplify this risk of failure to be this equation, 1 minus 1 over T to the power of T. So then we may wonder, well, how does this risk of failure looks like, right? So basically for most of the engineering systems, they're going to look like, they're going to have a risk of failure that sort of have the equation that looks like this. So then you may think that, well, the risk of failure is really going to be dependent on the T here, or this design life here. But it turns out that it's not the case. So for example, we can try to plot the PF as a function of T, right? Which is duration or the design life of this engineering system. For example, we can define, say, just create this new function here. The first one is about the risk of failure, right? So we can define this this design life, right? We can define it as, let's say, starting from 5 years and separate by 5 years into 100 years. Okay, so of course, shorter, let's say the design life is going to basically have a higher exceedance probability, right? So basically, it means that the system is going to be failure more, right? But if you have a high design life, right, the system is less going to be having a failure. So note here that we're calculating the risk of failure. We're evaluating the risk of failure over the entire duration, right? So because in that case, then we're just trying to look at the duration of failure, or the risk of failure over 5 years for this high probability of having failure, and also looking at the risk of failure for this low risk system over the period of 100 years. Okay, so if you plug in the specific values of t, right? So it will be 1 minus 1 dot divided by t to the power of t. Okay, so then we can plot t and pf. You see how it looks like. Okay, so this is our plot. So you can see that basically we're trying to plot the y-axis being the risk of failure, right? X label being design life. Okay, so you can see that no matter whether it's at 5 years or 100 years, basically the risk of failure for this engineering system always ran, uh, I mean, distributed in the range of 0.63 to 0.67, right? So they're quite similar. So basically the risk of failure is also going to be similar, no matter whether you're talking about, let's say, a highway system, right, that can theoretically hold for 100 years, or let's say a small scale water pumping system that has, let's say, a short lifetime of 5 years, because here we're evaluating the risk of failure over the design life, right? We're not talking about over the entire, let's say, 100 year. We're not comparing the same time period. Okay, so this is the risk of failure. And then we already did this plot over here. So this is the first definition, right? So we were talking about the risk of failure, but a lot of times in environmental engineering, or in all types of engineering systems, which we're trying to calculate the probability of a system that achieves certain type of property, right? So for example, you're talking about rainfall, right? So then it could be for example, the probability of rainfall with the rate of rainfall exceeding certain level, right? So, or if we're talking about the failure of the system, we're talking about, let's say, the risk or the probability of the system having, let's say, 2 failure within the first 5 or 10 years, right? So in that situation, we have to evaluate the probability. And a lot of times, it depends on what type of the probability distribution we're talking about. Okay. So basically here regarding the probability distribution, there are 2 definitions. So first is the discrete probability distribution, right? So we could have discrete probability distribution. We could also have the continuous probability distributions. So what the discrete probability distribution means is that the system can choose certain levels. For example, it's like you are rolling a dice. We know that the dice can only give you 1 through 6, right? You're not going to get 1.5 or 1.2 or any value between these discrete numbers. And then rolling the dice, let's say 1 dice or 2 dice, the probability associated with different results is also fixed, right? And we know that if you sum up all of these probabilities, they're going to be 1. You're not going to create let's say a 200% probability, because here we're talking about, let's say, the frequency, right? So the summation has to be 1. And based on that, the discrete probability functions, you can also calculate the cumulative distribution function. So what that means is that we're trying to get the summation. For example, again, rolling the dice, we're trying to find out the probability of the system that had of the dice results that has a value smaller than 4, right? Smaller or equal to 4. So basically, you're going to get the summation of the dice having the value 1, 2, 3, and 4. So that's the cumulative distribution function. Okay, so this is discrete probability distribution. And we could also have the continuous probability distribution. So for this scenario, we can be talking about the temperature, right? The temperature of the ambient environment. We know that, well, of course, for your measurement of the temperature, right? If it's a digital temperature or thermometer, you're only going to get the value of, let's say, 20.1, 20.2 degrees Celsius. But actually, the temperature can be continuous, right? And it's also changing, let's say, from early morning to noontime continuously. We're not seeing the temperature jumping from one temperature to another temperature, right? So this should be the temperature, if you think about it, should be changing continuously, right? So because of that, we can define this probability distribution, let's say the fx, right? So the fx defines the probability. If you're using the temperature as an example, it defines the probability of the system having certain temperature value, right? So for example, if let's say we're talking about in Miami, where the temperature is higher, right? So the overall, the frequency or this probability function of having value, let's say higher than 30 degrees Celsius, is going to it's going to be higher compared to the northern cities like New York. Okay, but at the same time, we know that this summation or the integral of this temperature probability function from minus infinity to positive infinity should be 1. Let's say if you're thinking about temperature on our Earth, right? So it should be minus, let's say, 233 degrees Celsius to, let's say, 100 degrees Celsius, because, or it could be higher, right? Because if you have a volcano, it could be thousands of degrees Celsius, right? But we know that the frequency or the integral of this probability distribution should be equal to 1. Again, we're talking about the probability values. You cannot have a summation or integral of the probability function higher than 100%. So similar to the definition of the cumulative probability function that we show in here, right? So we could also do this integral from minus infinity to a certain level. For example, again, about temperature, we could be looking at the cumulative distribution function, or the CDF, representing the probability of the temperature, let's say, below 30 degrees Celsius, right? For most of the places, this probability is going to be higher, right? Because we know that 30 degrees Celsius is considered to be hot on the Earth, right? I would say this cumulative distribution, cumulative probability is going to be higher than 50% for most of the places on our Earth, okay? And also, based on this cumulative distribution function, if you have the CDF, then what happens is if you take the derivative, it's just going to be the probability function. So you have this inverse relationship, right? So the CDF, the cumulative distribution function, is the integral of the probability distribution. While if you have the cumulative distribution, then you can just take the derivative to get the actual probability distribution. And further, basically, these are just general definitions in the statistics. Let's say if we're trying to calculate the mean value of a system, if it's a discrete system, again, talking about rolling the dice, right? So we know that the dice, if you roll it, the probability for each number is 1/6, right? So to calculate the mean, it's just going to be the dice number that you rolled multiplied by the probability of each number, right? So it's 1 multiplied by 1/6, 2 multiplied by 1/6, 3, 1 over 6, 4, 1 over 6, 5, 1 over 6, and 6, 1 over 6, right? You take the summation, and then you're going to get, what, 3.5, right? So this is the mean of the value for you to roll the dice, right? Consider all the probabilities. So the same thing for the temperature or for the continuous system. So continuous system, you just also multiply the actual value with the probability and do the integral. So we can be thinking about the average temperature. So then you have temperature multiplied by the probability of the system having that temperature, right? And then take the integral, and you're going to get the mean temperature of the system. And we could also calculate the variance. So variance describes how the values are being distributed, right? So if you could have a large variance, which means that basically it's going to have a high probability everywhere, right? You could also have a system that has very low variance, which means that most of the values are going to just concentrate at certain value. Okay, so the variance is calculated by basically the probability multiplied by the square of each specific value minus the mean value. So we're talking about the mean over here, right? So you can see that if you have a system that most of the values are close to the mean, then the variance will be very small. It can be 0, right? But you could also have a system, let's say, again, for the dice, because it's a uniform distribution among all the numbers. So the system is going to have a larger variance. So the same thing for the continuous distribution, right? Continuous distribution, you just change the summation symbol to integral, right? And then do the dx, right? Integral from minus infinity to positive infinity, and you can get the variance of the system. So there are a few more definitions related to the probability function, right? So people will also look at the skewness. So what the skewness means is that you could have a distribution of the probability, right? But the thing is that the shape of the probability is not always symmetric. You could have a system that, let's say, concentrate nearby 0, right? While it has a long tail in the larger ranges, right? But you could also have a system that has low probability and most of the values are concentrated at the higher values. So the skewness basically represents, let's say, the random outcomes occur that are either less than or greater than the mean, and the symmetry of these outcomes above mu x is measured by the skewness, right? So basically, how symmetric your probability distribution function looks like. And you can imagine if you're talking about the skewness, right? So we have to think about how far away, right? So for example, at the far away points, how does that influence the, so that's going to lead to a certain value, right? So you can see the way that we calculate the skewness is if it's a discrete random variable, right? It's going to be xi minus mu x to the power of 3 multiplied by fx. And then you divide the standard deviation to the cube on the left-hand side. So you can imagine if you're using the dice as an example again, right? So the dice has, we said, a large variance, right? Because they're not concentrated near the mean value. But at the same time, if you use this equation, because everywhere is 1 over 6, right? So then at the values smaller than the mean value and the values larger than the mean value, they're symmetric, basically. And then here, since you're taking the cube, they will eventually cancel out. As here, we're doing the summation. So basically, the rolling the dice scenario is going to give you a probability distribution function that has 0 skewness, right? So it's basically symmetrical on the left-hand side and right-hand side of the mean value, right? But then it could be that, for example, we're talking about the flow over a river. Well, most of the time, the river flow is going to be close to 0, right? Having small value. But every often there are, after some time, there could be, let's say, a flooding event that gives you really, really large values. It's going to have a very large tail. So under that situation, as you can imagine, we're going to have a large skewness for the river flow, okay? So this is for the, for the rolling the dice, this is about the rolling dice scenario is going to be a discrete distribution, right? But if you're talking about the water flow, that it has to be a continuous scenario, because water flow is not going to jump from one value to another value. It's always a continuous distribution. So we're going to use a similar type of equation, changing the summation sign to the integral sign to calculate the skewness. So in addition to the skewness, right? So you see here, this is to the power of 3. So people also define this kurtosis. So the kurtosis is a measure of the fraction of outcomes that occur near extremities of the distribution. So what that means is, for example, we're talking about, let's say, the distribution of the river flow, right? The continuous probability distribution. So there are places that are influenced by, let's say, more frequent flooding events. But there are also places that are less influenced by these extreme flooding events, right? So if you consider the extremities, so the kurtosis of this place that has less number or fewer number of the flood, right, it's going to have a smaller kurtosis compared to the other place, okay? And this is represented by the value minus the mean value to the power of 4, because we want to consider both the extremity on the left-hand side and extremity on the right-hand side. So if you're using temperature as an example, we can think about that too. So if you have a place that can be really, really hot during the summer and at the same time being really, really cold during the winter, then the kurtosis is going to be bigger. If you think about the location, such a location in the United States, maybe I would say the Midwest, right, central part of United States, it's going to be very hot during the summertime, right? It's continental weather. And then during the wintertime, there's always these cold front from the Arctic area. The temperature can also be very low. But then if you think about, let's say, California or San Francisco, right? So people know that the temperature distribution there is always quite narrow, right? But by having a narrow distribution of temperature, the kurtosis is going to be smaller compared to the Midwest, okay? But the thing is that for both places, they could have the same skewness, right? Skewness is talking about the symmetry around the mean value or the mean temperature. So we could also define the same thing for the discrete random variables, right? Like throwing the dice, so on and so forth. Okay, so these are the different definitions associated with the probability distribution function. So here, this is an example talking about the failure, the probability of failure. Let's say, if we recall in the beginning, we defined this probability of failure or risk of failure. So we can do a, let's say, a practice of how to calculate let's say, the probability associated with failure for the system, right? So if you read this problem, basically a water resource system is designed such that the probability Fxi, that the system capacity is exceeded x times during the 50-year design life, is given by the following distribution. So first, by looking at this description here, since we're talking about environmental system, or water resources system, there are some translations needed, right? So basically the Fxi, which is a probability, associated with the system capacity is exceeded xi times. So basically this is telling that the system fails xi times, right? The system can fail 0 times, 1 time, 2 times, 3 times, 4, 5, 6 over the 50-year design life. Okay, so if you look at this distribution, you can see that over the 50-year design life, it's more likely to fail between 1 and 2 times, right? So although 3 times is also a relatively high probability, but then the probability of failing more than 6 times is 0, right? It follows this probability distribution. And from here, you can also see that this is a discrete probability distribution, right? Because the xi, the times, this is not continuous. We don't have a system that can fail 1.5 times, okay? So although, well, the average of, or the mean of the expected fail times could be fractional, right? It could be non-integer. Okay, so we have this probability distribution, and then it's asking us what is the expected number of system failures expected in 50 years? What are the variance and skewness of the number of failures, right? So based on these definitions, we can do this quick calculation. Example 1. Right, so we know that x ranges from 0 to 6, right? And the reason why we don't consider more than 6 is that the probability is already 0, so we don't have to show the fx anymore, because if you see if the f is 0, then they're not being considered in this calculation. They're just 0, right? So we can also list the f value, which is 0.13, 0.27, 0.28, 0.1809. And these are the values. Basically, there are 7 values: 1, 2, 3, 4, 5, 6, 7. Okay, so we're trying to calculate the expected number of system failure, which is the mean of the system, right? So we could calculate, let's say, mu, because here we're using the mu, right? It's going to be the summation of x dot multiply f. Okay, which is 2 times. It happens to be that the mean value is an integer, but it could be that it's not an integer. Another thing that we want to sort of confirm is that here this is the probability of the f. So we know that the summation has also has to be 1, right? So we can check what is the summation of f, right? You see the summation of f is 1, so which actually satisfies the definition of the probability function. And another thing I want to mention is that if you recall earlier when we were talking about the matrix algebra or linear algebra, we said that we could sort of simplify this calculation. So there is a special function called the dot function. And you can just put x and f inside, and then it's going to return you the value. So from now on, let's just use this one because it's overall it's more simple. Right? So this is the mu, and then it also wants to calculate the variance. So the variance is going to be dot again. So it's going to be a dot multiplication of the f, and together with the square, or the, let's say, the difference squared, right? So it's going to be x minus mu dot squared. Okay, so then this is the variance. Skewness is going to be dot again. We know this is f, and then on the left hand side, right? So before this comma, if you see here, it's going to be the x value minus the mu value to the power of 3. And then at the same time, we're going to divide this thing by the variance to the power of 3. No, the standard deviation to the power of 3, because here, you know, the variance is standard deviation squared, right? So here, this one is the standard deviation cubed. So basically, we need to first take the square root and then multiply by 3, which is to get the cubic, right? So then it's to the power of 1.5. So then you can calculate the skewness is 0.6315. Okay. So I mean, since this one didn't ask us for what is the Curtis, but we can also calculate the Curtis. Right. It's going to be dot. And then again, it's f. Right. It's going to be dividing by the variance to the power of 2. And then here on the left is going to be the power of 4, and then x minus mu. Right. So if you calculate that, it's going to generate a kurtosis of 3.13, right, 125. Okay, so basically these are I would say relatively easy way to calculate the how the, let's say, the general properties of the probability distribution functions. Okay, so of course here we're using a discrete distribution. There could also be a continuous distribution, which involves the integration. which happens to be this case, right? So we can also confirm our numbers here, right? To 1.92, skewness 0.63. Of course, this one didn't ask us for the kurtosis. So this is next example. Here we're talking about the probability distribution function or probability density function. This is the time between rainfall events during the summer in Miami, right? So then we know that time between rainfall events. So of course, the time between the rainfall events cannot be smaller than 0. So that's why when t is smaller or equal to 0, that's 0. And when the time is larger than 0, then you have this sort of the power law or distribution or power distribution. Okay, so then where t is in hours, and then estimate the mean, standard deviation, and skewness of the t. Okay, so then we know that for the continuous distribution, then we need to do integral, right? So how do we integrate? We can basically use a function to use the integrate function, right? So this is the content that we learned from our last class, right? And then we could, that's numerical integration. And also we could use the symbolic mathematics to do the integration. And so here I will just try to show both of them. So the first is using the numerical integration. So we need to first define our function, right? So it's going to be f. Let's say f is going to be at, let's say t, and then it's going to be 0.014 multiplied by exponential minus 0.014 multiplied by t, right? So this is the probability function. And then just out of curiosity, we can do an integral of this probability function to see if it's really 1, right? So then we could also make it make this plot, let's say f. And then in the range of, let's say 0 to 1,000. Right, so this is how the function looks like. And of course, we can also change the y limit. Right, so y limit 0, let's say when time this is the f function. When f is equal to 0, or when time is equal to 0, right? So this is going to be 0.014. So let's do 0.02. Okay. So this is how the probability function looks like. And then, of course, we can do an integral and see if it's indeed 1. So we can do that by just doing, let's say, f, right? It's going to be integral of f. And then we need to define the beginning point, the ending point, right? So the ending point, let's put 1,000 over here. Right, you see, it's 1. So basically the probability function, when the time is like we're integrating from 0 to 1,000, is going to be 1. Okay, which makes sense because the probability function, the entire area below this curve had to be 100%. Okay, so now we can look at the mean, right? So this is basically the time between rainfall events in hours, right? So time between rainfall events, and then when it's the let's say close to 1 hour, right? Let's just show this plot again. So let's say when the time is 100 hours, right? If the time between rainfall event is 100 hours, then the probability is very low, right? But if the time between rainfall events is, let's say, 10 hours, it's going to be higher, right? Time between rainfall events being 0, it's 0.14. It's relatively small, right? So basically, this is telling us that in Miami, we are going to rain quite frequently, right? So then because of that, the longer time, the probability is going to be lower. So here we're trying to calculate the mean time between the rainfall events, right? So then what we do is we just multiply the time in front of the probability function. So we can define that as F1. Then it's going to be here. And then we multiply that by the time. Let's just put time over here. And we don't need to make the plot anymore. And then let's make here being integrating int F1, right? So this is the int F1, which is the mean time. So it's saying that, well, we have to consider the dot multiplication because remember, numerical integration is still using matrix calculation. So that's why we need to consider the dot multiplication, right? So we can run this. I think we probably need the dot over here too. Okay, so then this is the mean value. But one thing we should try is to also consider the larger range, because now we're only integrating to 1,000. It could be that when we integrate to really, really large values, the integral still changes, right? So you can see when we change from 1,000 to 100,000, it increased by a little bit. We can try even longer time. It doesn't change anymore. So basically, it means that we're not integrating until infinity. And this is just the mean time, right, between the rainfall. And so then we can also calculate the, let's say the standard deviation, right? The standard deviation is going to be the time minus int F1 to the power of 2. Right? And then you multiply by the probability function. So here is going to be F2 into 2. Right? So this is going to be the standard deviation. And then the skewness is just F3 into F1 to the power of 3. Right? So we have to integrate F3. And then at the same time, don't forget that we need to divide the value by the variance. Right? So it's going to be into F2 to the power of 1.5, right? Because we're dividing that by the standard deviation to the power of 3. So this is into F3, right? So it turns out that the skewness is 2. Okay, so basically, I mean, we were talking about the mean time between the rainfall events. Actually, the mean time is just going to be the int F1. It turns out to be 71 hours. If you think about the time here, basically it represents around 3 days, right? So you will say that this is still a relatively frequent precipitation events, right? Every 3 days it rains, right? I would consider it's quite frequent. Okay. So basically here, this is how we can calculate it using the numerical integration. But we also said that we could use the symbolic mathematics, right? So symbolic mathematics is going to be similar. You just need to define sims, right? And then t, and we don't need to define f, actually. So let's see here. We just need to clear the memory, right? So then let's create a new section. So we don't need to rerun everything. So here, instead of using the integral function, we said that if it's numeric, if it's symbolic integration, we actually use the int function, right? So then we could just do int. And then here, we don't need to create this at, right? Because we're using the t here. And then this is the integral. And the thing is that, oh, well, let's see, we can try to run it first. We can use the int function. Okay, so for the first one, we can also integrate it in this large range here. So if we run it, right, see, this is what we get. Basically, numerical integration is going to give you the analytic solution, right? It's not a numerical solution. Everything is symbolic, right? At the same time, if you see these values, it exponential to the minus 140,000. This is very, very small, right? So basically, it just represents that the probability function integral is 1, right? The same thing here. A lot of these values are multiplying a very, very small exponential value, okay? So how do we convert the analytical form into a numerical form? We just use double, right? We sort of force it to become a double number. Recall, we're using this definition in the data types, right? So double, and then double. So now you can run it. We'll see what we get. Right? 72 hours or 71 hours, around 3 days. Right? This is variance, and this is the skewness. Okay, so here I'm also including solution. Right? So, of course, if you don't know MATLAB, you sort of have to integrate everything by hand, which is going to take quite a lot of efforts. Right? So some of them may even be let's say there's no analytical solution. You have to use some software to do the calculation. One thing I want to point out that here, this is a typo. It should be 2.0. Okay, so here we introduced two scenarios. One is a discrete probability function. The other is a continuous probability function. But actually, in engineering systems, there can be all different types of probability functions. And there are, for each one of them, there is actually some physical meaning behind them. Okay, so here we're just going to introduce several, I would say, relatively common probability distribution functions. And then we'll also do some simple practice with the calculating, let's say, the probabilities. Okay, so if you think about any probability function, it has to satisfy two conditions. First, it has to be non-negative because a negative probability does not make sense, right? Everything has to be above zero, at least close to, being zero or above zero, right? Non-negative. And the second is that it integrates into unity, right? So we showed that in our first example problem, right? So we did a summation of all of the values and it's 1, right? And then the second one, we did the same thing because if you integrate f directly, you get 1, okay? So basically, these are the two conditions, right? So you could even define your own probability function as long as they fit this definition. But in engineering, especially environmental engineering, there are certain types of probability function that we use more commonly, right? So here I'm just going to introduce several of them. So the first one is the binomial distribution or the Bernoulli distribution. So basically, the background is that many engineering systems are designed to operate below certain threshold of design conditions. So basically, we're talking about this, the success of the system or failure of the system, right? So specifically, the binomial distribution function describes the probability of the system having n successes in a capital N number of trials. For example, you could have 10 trials, right? Let's say 10 years, right? So then the system succeed, right? Works in, let's say, 5 years, or the system break down in 5 years or in 2 years, given that the output in any one trial is independent of the outcome in any other trial. So basically, we're talking about, let's say, over these 10 years or 20 years or any like number of trials, right? So we're selecting certain cases or certain trials having certain type of outcome, right? So basically it's a selection. That's why you have the factorial n divided by lowercase n divided by capital N minus lowercase n, right? The factorial. And then you multiply that by the probability specifically. Okay, so then basically this is the binomial or Bernoulli distribution. So we're going to give an example later on. So basically for this discrete probability distribution function, the mean value is going to be the capital N multiplied by P, right? And standard deviation and the skewness are going to have these values. So this is an example. So the capacity of a stormwater management system is designed to accommodate a runoff event with a return period of 10 years. Right? Return period of 10 years means that the exceedance probability is 1 over 10, which is 0.1. It's going to fail on annual basis. There is a 10% failing rate. Right? What is the probability that the stormwater will fail once in 20 years? So if you think about the definition here, so basically in 20 trials, right, 20 years, it failed for 1 year. Right? It failed for 1 year. What is the probability that the system fails at least once in 20 years? Right? So fails at least once. Basically, it's going to be more than once, let's say 1 time, 2 times, 3 times, 4 times, all the way to 20 times. But then you can also just exclude the scenario that it didn't fail at all in 20 years, right? So then based on these definitions, we can calculate the probability, right? This is example number 3, right? So we know that we're talking about the probability P, which is the exceedance probability is 1 over 10, because it has a return period of 10 years, right? So the exceedance probability is 1 over 10%. And then the capital N we're talking about is 20 years, right? So the number of this event happening, first we're talking about one event, right? So then F basically is going to be factorial of N divided by a factorial of lowercase n divided by factorial capital minus lowercase multiplied by P to the power of N multiplied by P, or let's say 1 minus P to the power of N minus N. Okay, so it looks like we used a capitalized P here, right? So this is the probability of having one failure. So what is the probability of the storm of water fail at least once in 20 years, right? So we just need to use, let's say F0, this is F1, right? F0, same thing. And now we define N being 0, that it doesn't fail, right? So then the probability we're looking at, let's say this capital P, is going to be 1 minus F0. It doesn't have any failure, right? So then the probability of the system fails at least once is going to be 0.8784, which is relatively high, right? So this is a Bernoulli distribution or Bernoulli probability function. Okay, so if we look at the definition here again, so specifically the binomial or the Bernoulli distribution function describes the probability of n successes in capital N trials, given that the outcome in any one trial is independent of the outcome in another trial, right? So basically we're talking about the system getting failed, and then we're replacing the system with a new system that has the same return period, right? So it's not influencing the probability of the downstream process. And another thing here it points out is that the probability of n successes, but actually it should be n occurrences, right? So probability of n occurrences in n trials, given the outcome in any one trial is independent of the outcome in any other trial, and the probability of a occurrence in any one trial is P, right? Okay, so that is the let's say the binomial distribution. So you may be interested in, let's say, if we're talking about the system, right, that can run for 10 years and we run it for 20 years. What is the probability that fails at each specific time, right? So if it fails 0 time, we say that it's around 12%, right? If it fails 1 time, it's around what? It's around 0.27, which is 27%, right? So can we plot the probability function as a function of the failing times, right? So we can try to do that. And here, we can use a for loop, right? So basically, we can define for being n having the value of 0, 1, 2, 20, because it can fail 20 times every year, right? Within this 20 years. So then we can have the P, F, let's say n plus 1 being this whole thing here. Right, every time the n changes its value, and then you're going to have a new f, right? Then you can plot 0, 1, 20, then f. Okay, so this is how the probability function looks like. So you can see that on average, right? So the number of times the system will fail is at its peak when it fails 2 times, which sort of makes sense, right? So return period of 10 years, it means that every year it has 10% of failing, right? So over 20 years, on average, or I would say the maximum value that the highest probability is going to be the system fail for 2 times. But you can also see that from the probability function, you can predict the frequency of the system failing 3 times, 4 times, 5 times, so on and so forth, right? So each of them still have a value. Let's say it can also fail for 14 times, right? Fail for 20 times. Okay. And the other thing we can sort of test is that now we have the f, which is the probability, right? So what about the summation of f? So you can do a summation of f, right? It's 1. It's 100%, right? So this is the binomial distribution. So basically, the summation of all of these probabilities from 0 to 20 is going to be 1, right? 100%. Okay, so this is the binomial distribution. Another distribution people commonly consider is a geometric distribution. So the geometric distribution is a discrete probability distribution that describes the number of Bernoulli trials, right? So n, which is sort of the big N that we used here, right? So the number of Bernoulli trials up to and including the one in which the first success or first occurrence happen, right? So one example can be, I mean, talking about the failure of the success, right? So it could be like how many years until the system fail, right? So the probability of having the system set up for 1 year, it fails, right? Set up for 2 years, that fails for the first time, or set up 3 years, right? You run it for 3 years and it fails for the first time, or run it until 100 years and then it fails for the first time, right? So if you consider the probability of the system running for 100 years and fail for the first time, you would say that, well, this is jackpot, right? Because we know that the system has a 10% of failing rate every year. And the thing is that it ran for 100 years. So another example can be you're flipping a coin and the head appears for the first time after n trials, right? So note that here, this lowercase n is a capital case n in here, the number of trials. So basically, it's the probability of certain condition that occur for the first time over the n number of trials. Okay, a similar example can be, let's say, a stormwater management is designed for a 10-year runoff event, right? So The P is going to be 1/10. What is the probability that that capacity of the stormwater management will be exceeded? Basically, the system fails for the first time in the 5th year after the system is constructed, right? So basically, the system has a 10% failing rate every year. What is the probability of the system failing until the 5th year that it starts to fail? Right. And that's section B is what is the probability that the system capacity will be exist within the first 5 years? Right. It could be failing in the 1st year, 2nd year, 3rd year, 4th year, and 5th year. Right. So then for that, you need to consider a summation. So this is example 4, geometric distribution. Right. So then basically based on this definition, we're talking about P being the value of 1/10. Right. Let's also clear the memory. So in case there are confusions. Right. So then the system fails for the 5th year, first time in the 5th year. So it's going to be F5, right? Being P multiplied by 1 minus P to the power of 5 minus 1. Right? So then fails for the first time is 0.0656. Right? And then what is the probability that the system capacity will be exceeded within the first 5 years? So you have to consider the scenario of fitting the 1st year, 2nd year, 3rd year, 4th year, and 5th year. Right? So you can calculate F1, F2, F3, F4, F5 separately. Right? So let's do that. So 4, 3, 2, 1. Right? So here you're going to have 4, 3, 2, 1. And then you can do the summation. That it's 0.4095. But the easier way we know is to basically do a for loop, right? So you can do for n being 1 through 5, right? And then f of n being p multiplied by this term n minus 1, right? So then we're talking about sum of f, right? So it's the same thing, 0.4095, right? Another thing is that we can try to plot the probability in each year, right? It fails for the first time in each year. So the same thing here, right? So you can do a for loop. So let's hide all of these. So we can define this. And then because we're talking about let's say design for a 10-year runoff event, what's the probability? So basically there's no upper limit, right? It can run for 100 years and still not failing. So let's just put 100, maybe put 50 because 100, the value will be so small. So then Fn being P multiplied by the term here. Right, and then you can run it from 0 to 50. P, okay, it starts from 1 because the system had to run for 1 year to know whether that whether it fails or succeed, right? So then this is how the distribution looks like, geometric distribution, right? So it's more likely to be failing in the 1st year, right? So, but the thing is that when you consider the average running period, right? So it's going to be this probability multiplied by the years that they have already run. So then the average or the mean lifetime can be longer. But you can see that there's a higher probability that the system fails in the first year, which makes sense because here you see we're multiplying by a probability that's smaller than 1, right? So the largest value is going to happen when n is equal to 1, which is just p. Okay. So there are other types of basically the probability distribution functions. I would say this one, you probably have heard of it before, which is a Poisson distribution, right? The Poisson distribution is a probability distribution of the number of successes or occurrences n in an interval in which the expected number of occurrences is given by lambda, described by the Poisson distribution function. So what it really means is that basically we're trying to conduct a number of the trials, okay? But at the same time, we know that the system, let's say, has a, let's say, a duration time or the return time of 100 years, right? A return time of 100 years, that means the probability is 0.01. But then the thing is, we're interested in the probability that the system fails within 50 years. We're not interested in this entire 100 years, right? So then the distribution is going to follow this Poisson distribution. Another example can be we're flipping a coin for n times, right? So we want to count how many times the head appears. I mean, the probability of the head appearing m times, right? So that also follows the Poisson distribution. Okay, so the way you calculate that is first, if you're talking about a discrete distribution, what happens is that the probability function is going to be equal to lambda, right? So remember, lambda is the larger n multiplied by p. Okay, so we said that the larger n is the number of the trials. Okay, and the p is the basically the probability or the exceedance probability, right? So first you can get the lambda, and then so basically the time of occurrence happens in, let's say, n times within this. I mean, happening with lowercase n time within this larger uppercase n trials is going to be calculated by this equation. Okay, so this is for a discrete distribution function. So we can do a practice first, right? So you'll get to understand what it means by lambda and what it means by lowercase and uppercase n. So for example, we're talking about a, let's say flipping a coin, right? So flipping a coin for n times and the head appears for lowercase n times. So maybe I shouldn't use all of these different symbols, right? N times or O times. Right, so it could be flipping a coin for 10 times and the head appearing for 5 times, right? We know that it's going to be the highest probability. So then to calculate the probability, it's just Fm, right? So we know that we have to find out the lambda first, right? So lambda is the uppercase n, which is 10 times multiplied by the probability, which is 50%, okay? So then lambda is 0.5n and to the power of n, right? So how many times you want it to happen, right? Head occurs for n times, right? And then multiply by exponential minus lambda, right? Divide by factorial of n, right? So for example, we can try to plot the probability of the head happening from, let's say, 0 to 100 when you flip the coin for 100 times, right? So flipping coin, right? Poisson distribution, right? So we know that we're talking about n being 0 to 1 to 100, because when you toss a coin, it could be that the head appears 0 times or the head appears 100 times, right? The same thing, let's say if you're talking about the system fail, let's say, then can not fail at all, right? The system can also fail every year, right? So then basically you can calculate the f, n plus 1 is going to be 0.5 multiplied by n. We're flipping the coin for 100 times. So it's going to be 0.5. Let's do P, right? P, we know that it's 0.5 because each time when you flip the coin, it's 50% head or 50% tail, right? So it's P multiplied by N to the power of N multiplied by exponential minus, right? And then divide by factorial of N. And plot. And then F. So this is how the distribution is going to look like, right? So this is basically a Poisson distribution, right? And then when you flip the coin, you know that if you flip it by 100 times, then the highest probability is going to be 50, right? And then it's going to decrease, right? Both on the smaller side and on the larger side, right? So there is also a probability that you don't have any head, right? So that's going to be very, very low. Okay, so this is a total random process. So we can use the same idea to consider this example, right? So a flood control system is designed for a flow with a return period of 50 years, which means that P is going to be 1 over 50, right? That's 0.02. Assuming that the exceedance of the 50-year flow is a Poisson process, what is the probability that the design event will be exceeded twice within the first 10 years? So now you see, we're not talking about the entire 50 years. We're talking about 10 years, right? So which is smaller set. But then this is 10 trials, right? So the capital case N is going to be 10. So this is example 5. So first P is going to be 1 divided by 50. And then the trial is actually 10. There are 10 trials. So lambda is going to be, let's just do LBD. P multiplied by N, right? And then it's trying to see what is the probability that the design event will be exceeded twice in the first 10 years. So we know that N is going to be, lowercase n is going to be 2, right? So F2 is going to be LBD to the power of 2 multiplied by exponential minus OBD and divide by factorial. Let's clear all of the memories, right? So P multiplied by N. So lambda is going to be 2 ohm, well, 50, right? Factorial N is 2. And then it should be to the power of N, right? So basically P is 1 over 50, and then N is 10 years. We're talking about 10 years, right? So lambda is basically P multiplied by N, right? It's going to be 0.2, and then 0.2 to the power of 2 multiplied by exponential minus lambda divided by factorial of N, right? So basically it's the design event will be exceeded twice, right? In the first 10 years, right? So this is the answer. And then you can also calculate what is the probability that the system will exceed more than twice in the first 10 years, right? So if it's more than twice, so basically it's going to be 3 times, 4 times, 5 times, so on and so forth. So we have to consider the other way. It's going to be more simple. So we can calculate what is F1 and F0. Okay, so then we can do, let's say, 1 and n equals 0. It doesn't happen at all. Do these, right? So then it basically exceed more than twice. It's just going to be 1 minus F0 minus F1 minus F2. Right, so it's going to be basically these three, right? So you can see the difference from this problem compared to the problems earlier is that these problems considers within the entire lifespan, right? Entire design life. But here we're converting this entire lifespan into a smaller subset and then trying to describe the probability and for different scenarios, right? So this is a major difference for the Poisson distribution. And then they're going to follow the equations that we introduced about. Okay, so just trying to confirm the numbers, right? F2 is going to be 1.6%, and then if the probability that the system will exceed more than twice or fail more than twice is going to be 0.1%, which is really, really low, right? So you see, basically that also makes sense because the return period is 50 years, so it's 2% failing rate. So within the first 10 years of the system failing, it's going to be very, very low, right? So zero failure is going to be 0.82, right? So it's 82% of the system not having any failure. Okay, so so you can easily, let's say, expand this scenario into, let's say, you bought a washing machine and the washing machine is designed with a let's say um, return period or lifetime of 20 years, right? Theoretically, you can use it for 20 years. And then basically you're lending this washing machine to a friend for 5 years, right? So then she wants to find out, or she or he wants to find out what's the probability of the system failing within the first year, within second year, third year, fourth year, and fifth year. And the summation have to be 1, right? Because you cannot easily translate this into of a 50-year or 20-year probability into a 5-year probability. So because of that, we'll use the Poisson distribution. Okay. So after that, there's also this exponential distribution. Exponential distribution already showed this earlier regarding the Miami rainfall, right? The time between 2 rainfall events. And so we find out that estimated time gap is around 3 days, right? So actually, this is exactly the usage for the exponential exponential distribution. So the exponential distribution describes probability of the distribution of time between occurrences of an event in a continuous Poisson process. So for example, basically we use this exponential distribution to describe the time between rainfall events, like the one that we showed earlier. And then if you take, let's say, the integral, calculate the mean, it will give you the mean gap between 2 rainfall events. And then we could also calculate the probability of events less than certain duration. So if you think about what it means here is that basically we're trying to calculate an integral, right? So the duration can be, let's say, half a day, right? A third of a day, right? Let's say within 2 days, the probability, let's say, of rainfall events in Miami happening between 2 days, right? Or within 2 days, then it's going to be an integral of this function from 0 to 2, right? So within 5 days, it's going to be 0 to 5, right? So basically, you can see that with the integration range becoming bigger and bigger, let's say to 100 days, right? Probability of rainfall events with gap less than 100 days is going to be almost 100%, because we know that the rainfall are quite frequent here. So it's very unlikely for the rainfall to have a gap of more than 100 days, right? So you're going to get larger and larger values for the probability of events less than certain duration, right? So because of that, we can do this practice here. So this is example 6, right? So in the 86-year period between 1903 and 1988, Florida was impacted by 56 hurricanes. Assuming that the time interval between the hurricanes given by the exponential distribution, what is the probability that there will be less than 1 year between the hurricanes, right? So we're talking about this integration here, probability of events less than certain duration. So basically, it's an integral of the ft, then you have the larger ft, uppercase ft, right? 1 minus exponential minus lambda t. Another thing I want to point out is that for the Poisson distribution, you see here, this is the function, but earlier when we were calculating this case here, there isn't t here. So it turns out that for Poisson distribution, if it's a discrete distribution, we actually use this function here. If it's a continuous distribution, we'll actually use this function, which involves the t here, involve the time here. So here, I want to also point out that lambda has a different meaning in terms of the discrete distribution or the continuous distribution. So in the discrete distribution, it's just the product of the number of trials and the probability. But in the continuous distribution, lambda is the average rate of occurrence. So for example, if you're talking about flipping the coin, right, the average rate of occurrence is just 50%, right? So you see, this is different compared to what we mentioned, what we meant here, right? So this is basically the probability of the event on a unit basis, right? So if you consider this to be the case, which will involve the t calculation here, so lambda is going to be the average occurrence of the rainfall, right? Which is going to be 56 divided by 86, right? So lambda is going to be 56 divided by 86, right? So then we can use this function here. So basically the f is going to be 1 minus exponential minus d multiplied by first problem. What is the probability that there will be less than 1 year between the hurricanes, right? You just multiply that by 1. And then this is basically 48%, right? The probability that there will be less than 1 year between the hurricanes is close to 50%. Okay, so which sort of makes sense because you see there are 56 hurricanes, right, over 86 years, right? So then it's going to be sort of, although it's not one event per year, but this is a random process, right? So that's why this probability is below 50%, right? So yeah, that's why the value is below 50% because you don't have hurricane event every year. Okay. Second, what is the probability that there will be less than 2 years between the hurricanes, right? So then this is 1 year, and then you can easily calculate the event or the probability of less than 2 years. You just replace 1 by 2, right? This is 73%, right? So basically, the probability that there will be less than 2 years between the hurricanes is going to be 73%. Right, so this is the what we mentioned, the exponential distribution, right? This is still talking about Poisson process, but then here pay attention that we're describing this continuous process where lambda have a different meaning here, right? Lambda is the average occurrence rate, which is sort of the probability. Okay, so there are also other probability functions. So here I'm just introducing you the common ones, right? So the next one is a Gaussian distribution. We sort of mentioned about Gaussian distribution earlier when we were talking about making the plots, right? So, or fitting the curve. So the Gaussian distribution or normal distribution are symmetrical bell-shaped curve describing the probability density function of a continuous random number. So we said that the score of the students can be Gaussian distribution. The temperature at the location can be Gaussian distribution, right? The sea level can be a Gaussian distribution. The only issue, I mean, normally the Gaussian distribution have a value that looks like this, right? The equation looks like this. The only issue with the Gaussian distribution is that if you consider certain variables having negative values, right? So it could still generate you a certain probability. So for example, if we're talking about the annual rainfall at a specific location, right? So the annual rainfall, and we're talking about the statistics over the past 200 years, right? For example, for Miami, the annual rainfall can be relatively high, right? Let's say maybe 1,000, or let's say 1 meter per year, right? In total, the average rainfall. So then the thing is, if you think about this, and if we're trying to fit that with a Gaussian distribution, then even if you plug in a negative rainfall, you will still have certain probability. So that's an issue for the Gaussian distribution, which is negative values. But people find out that if the mean of the random variable is more than 4 times greater than its standard deviation, which means that the distribution, the bell shape, is very narrow, then errors in the Gaussian distribution assumption can be neglected. So what it means is that, for example, if we're talking about the distribution of the rainfall in Miami, right? So it could be that the rainfall mostly exists here, which we say is around 1 meter per year, but then it's really far away compared to the 0 point, right? At the same time, it's the mean value is much larger than the standard deviation, right? More than 4 times greater than the standard deviation. Then we can ignore the probability of having negative rainfall level, right? So this is another example, right? So you can do find out that the annual rainfall in this river basin in Central Florida has been estimated to have a mean value of 130 centimeter and standard deviation of 15.6 centimeter. So you can see this is more than 4 times, right? So we can use the Gaussian distribution. Assuming the annual rainfall is normally distributed, which is a case that we're trying to work on, what is the probability of having annual rainfall less than 101.6 centimeter? So we're talking about the mean being 130, right? So we're talking about the probability of the annual rainfall less than 101.6. Okay, so if we're thinking about less than certain level, we're also thinking about the integral, right? So basically, you're integrating the probability function from 0 all the way to 101.6, right? So since you're talking about the integral, we have to use the integration function. So here I will just skip the symbolic mathematics. So let's just define f being here, CLC, f being a function of x, 1 over sigma, define sigma, or just s being 15.6, and then mean or mu being 130. So it's 1 divided by s divided by 2 multiplied by pi to the power of 0.5 multiplied by exponential minus 0.5 and to the power of 2. X minus m, and then this divided by s. Okay, so this is the f function, and then we're trying to integrate it. So p, the probability is going to be integrate, or integral of f from 0 to, let's say, 1 or 1.6. Right? So you see the probability is very low. It's 3.4%, right? Which also makes sense because you see the standard deviation is very narrow, right? So that's why we can guess that the probability of the rainfall being smaller than 1 or 1.6, this is already like outside 2 sigma, right? Close to outside 2 sigma. And then the probability is going to be low. So we could also try, let's say, what's the probability of rainfall smaller than 130, right? So it's 50% because bell-shaped log normal distribution, it has a symmetric function, symmetric shape, right? You can directly get the probability being 50%. Okay, so as we mentioned, well, there could be scenario that there are negative values for the Gaussian distribution, right? Negative values for the rainfall. So that's why people created function called the log normal distribution. I think we also showed this earlier when we were trying to talk about the curve fitting, right? So for the log normal distribution, there are expressions shown in the log term or shown in the log 10 term. So if you look at these equations, basically, they have these sort of like factors, sigma y or log 10, mainly because we have to make sure that the integral is 1, right? If you do not include these constants, the integral will not be 1, and it won't satisfy the definition of the probability density function. So for the log normal distribution, if it turns out that many hydraulic variables exhibit a marked skewness, largely because they have a lower bound of 0. So what it means is that if you think about, let's say, the number of hurricanes every year, right? So most of the probability is going to exist at the location where there's no hurricane, right? So it has a high skewness. And whereas a normal distribution allows random variable to range without limit from negative infinity to positive infinity, the log normal distribution has a lower limit of 0. So log normal will basically limit the x cannot be smaller than 0. Okay. So this is where people will actually apply the log normal distribution. And after that, I think this is the final distribution that we're going to talk about, which is the normal distribution. The normal distribution describes the behavior of a random variable in which all the possible outcomes are equally likely within the range, which is very easy to understand, right? So basically within this range here, the probability is just 1 over b minus a. Again, the reason why we have 1 over b minus a is because the product, the integral of this function in this range here has to be 1, right? The height of the function multiplied by the base of the function b minus a, right? It's 100%. Okay, so the example can be conflicting data from several remote rain gauges in a region of the Amazon basin indicate that the annual rainfall in 1987 was between 810 and 1080 millimeter, assuming that the uncertainty can be described by a uniform probability distribution, which is kind of wild, right? Because it's rarely uniform distribution. What is the probability that the actual rainfall was greater than 1000 millimeter? So you can see basically if it's greater than 1000 meter, right, you first find out what is the probability density function. Okay. So F here, so C. So F is going to be 1 divided by 1080 minus 10. Right? So then the P is just going to be F multiplied by 1080 minus 1000. Right? So this is the probability that the rainfall was greater than 1000 millimeter by assuming that this is a uniform distribution. Okay. So these are the common probability density functions. So I think this is the earlier function that we already showed. So we don't need to show this one anymore, work on this one anymore. But actually, the distributions are more than these ones that we already showed, right? So it turns out that I could just quickly type in some of the distribution functions. For example, there are a function called the gamma function, right? So the gamma function, they also have different types, or let's say the Pearson distribution, gamma distribution, right? So there are, let's say, even for the gamma distribution, there are 3 parameter, or 2 parameter, or 3 parameter gamma distribution. Okay, so Pearson distribution, there's log Pearson type 3 distribution. So then let's see, further you could have a 3-parameter log normal distribution, extreme value distributions. And then further under extreme value distribution, basically it's trying to quantify the probability under extreme values. Okay, but there are different types. There are type 1, 2, 3. Okay, so further you could have a let me see the general type probability let's say the general type extreme value distribution, generalized extreme value distribution, or what people call as GEV. Okay, so and then there is the generalized Pareto distribution, and chi-square distribution. So you can see basically for engineering systems, there can be many types of distribution. And here we're just covering some of the common ones, or the ones that we can do some practice here. And again, you can see that for a lot of these calculations, we can easily use MATLAB to either do the integration or do the calculation. Okay, so that's why, I mean, in terms of your homework, please continue using MATLAB and then try to understand these different types of the probability density functions and also the probability calculations. Okay, so that's it for this class, and let me know if you have any questions.